is the electromagnetic wave, right? So sometimes we need to look at the spectrum domain, right? Sometimes we need to look at the time domain. Sometimes we need to look at the spectral domain. So we need to understand the Fourier transform. So this is a review of the Fourier transform. So this is the it's no good. Okay. Okay, let me look for this one. Not good neither. Let me see. Oh yeah, this one is much better. Okay, so Fourier transform. Fourier transform. Can you all see this? Right? Okay, great. Thank you. Okay, so the Fourier transform. Let's look at the GT. GT as the function in time. Right? So GT as the function in time, capital G omega. Capital G omega as the function in frequency. Function in frequency. Right? So GT is the function in time, capital G omega is function in frequency. Right? The Fourier transform is the Fourier transform of this GT. G little gt is the capital G omega, right? The Fourier transform. And we will use it as the negative infinity gt exponential I omega t dt, right? Fourier transform, and then the inverse Fourier transform of capital G omega equals the little gt, right? Little gt, and then this will be the 1 over 2 pi. There's a factor of 1 over 2 pi, and negative infinity, the G omega exponential negative I omega t d omega, right? D omega. Okay, so I want to point it out in some convention, which we will cover later on. In some convention, we have negative here. We have negative here for the Fourier transform, and we have positive, in front of I in the exponential, right? So we will change sign, negative I omega t here and positive I omega t here. So it's just different convention. We will cover later on, but just keep in mind this is the convention we're going to use at least for this class, for today's lecture. But there are other convention which has a negative there and positive there, right? Just be aware. Okay. Okay. So what is omega, right? So omega is 2 pi f, right? 2 pi f. That's the angular frequency. Right? That's the angular frequency. So that's the 2 pi f, right? So if we think that our frequency is 1 kilohertz, right? 1 kilohertz, then our angular frequency will be 2 pi, right? 6.28 kilohertz, kilo, right? To 2.68, yeah. 2.68 kilo, right? Okay, radius per second. Okay, note. So let's look at the some property, right? Let's do some property. If gt is a real function. Right? So if gt is a real function, right? Let's see what happened here. If gt is a real function, then let's say what kind of property it is, right? So if the gt is the real function, this is the real function, then let's see if gt is real function. Let me write here, right? Okay, if gt is the real function, then let's say g omega. Let's take a conjugate, right? Let's take a conjugate. Then take a conjugate. We should take a conjugate on the right-hand side also. So that will be negative infinity, infinity, the gt, and then gt conjugate, right? Okay, so I omega t, let's make a conjugate, and gt is real. So whether I take the conjugate or not, they're the same, right? Little gt conjugate equals little gt, right? Because it's a real function. And then dt, right? Then dt. Okay, so that's the capital G omega conjugate. So according to the original function, right? According to the original function, if we have, let me mark here. So this is my original function, right? This is my original function. It's actually the definition, right? It's the definition. So if we look it up, compare the original function and this function, we basically, the only difference between those two equations is the negative sign, right? It's the negative sign. And then, so if you put the negative there, you can just simply assume the omega is replaced by negative omega, right? The omega is replaced by negative omega. So it will be g negative omega, right? So it will be g negative omega. It will be g negative omega. Okay. So that means if I take a conjugate, it will be the g negative omega, right? So you probably will think, for the real part of the g, they are the even function, right? For the real part of the g, capital G, it's an even function. For the imaginary part of the capital G, it's the odd function, right? So that has this property. So if my little gt is a real function, then my Fourier transform satisfies this property. Okay, now let's say if gt, right? So if little gt is a real and even, right? Is real and even. It's a real function and it's a even function, right? So let's say if my little gt is a real and even function, what happened on capital G omega, right? So let's say if it's real and even, then now my capital G omega, right? My capital G omega is the real and the even. So let me actually write it as negative infinity, infinity, gt. I'll break this exponential apart, right? So this exponential I omega t is cosine omega t plus I sine omega t. So that it's Euler's formula. It's the Euler's formula. Exponential I omega t is cosine omega t plus I sine omega t. So we will separate the exponential I omega t by two parts. One is the cosine omega t, another one is the I sine omega t. So we will separate out the integral into two integrals, right? So one is the cosine omega t dt. Another one will be plus I negative infinity infinity gt sine omega t dt. Right? Okay, so we will add those two together, right? So we have two pieces. Right? Okay, so first, can anyone tell me what is the value for the imaginary piece? Anyone has an idea what is the value for the imaginary piece?
Is it 0?
It will be 0. Thank you. Very good. It will be 0, right? So this will be 0. Why? Because GT is the real and even. GT is the real and even. Sine omega t is an odd. So an even function times an odd function, there will be odd, right? So let me just draw a picture. So it will be an odd function. It will be look like this, right? And will be look like this. It's a sine function, for example, right? So an even function times an odd function, it is an odd function. You integrate over negative infinity to the positive infinity. This cancel out, so that will be 0, right? This will be 0. Now we can see this is an odd function, right? So we are multiply a integral a gt cosine omega t, right? And cosine omega t is an odd function. I'm sorry, cosine omega t is an even function, right? So this is an even function, right? Even and then real. Hopefully you all can see I'm writing even and the real. That's probably the corner, the corner you're able to see. Okay, so that is the g omega is the even and the real, right? So if the little gt is real and even, the capital G omega is even and real. Okay. Okay. Now let's look at. Let me borrow the space on the top. Okay. So let me. By the way, please write it down. Right. Please write it down so you can review your notes. So please write it down. Yeah. Okay. So you have everything. I mean this. I feel like this process of writing down give you another way of memorizing the material, right? Okay, let's say if gt, little gt is real and odd, right? And then g omega is this. Let's say is negative infinity, little gt cosine omega t dt plus I negative infinity gt sine omega t dt. Right? So now we separate out two pieces again, and then we have cosine omega t dt, sine omega t dt, right? But this time it's real and odd. So we have the real and odd times even, this become an even function, right? If I integrate over this function, then it will be 0. This time this will be 0, right? This time this will be 0, and then since we have sine omega t is a odd function, is an odd function, so overall this gt is imaginary, right? So g omega is imaginary. Gt is imaginary. Sorry, I kind of write it badly, but g omega is imaginary, right? An odd function, right? G omega is imaginary odd function. Okay. Okay. So now let's take a look at the last one, right? If gt is complex, right? If gt is complex, just the complex function, right? What happened here? So it will be the Fourier transform of the gt conjugate, right? Fourier transform of the gt conjugate. So that's the gt, right? Conjugate. Let me write it down. Let me see how to write it. It's the Fourier transform of the conjugate, right? Okay, so that is we'll just use this equation, right? The Fourier transform of gt conjugate, which is negative infinity infinity gt conjugate, right? Exponential I omega t dt, right? It's the I omega t dt, right? Okay, so now we will have this, now let's look it up, right? So it is the conjugate. So if I take a conjugate here, if I take a g omega conjugate here, then we have gt conjugate. Then we have another negative, right? Let me put the negative there. So it is the negative omega, right? So if I put a negative, so I put a negative g, then it will be this equation, right? Okay, so this is equal to g conjugate, right? If I take a g conjugate, then we have the little gt conjugate, but there will be a negative, right? So let me write a g omega. So be aware, what is this, right? What is this? Let me write it down. What is the g conjugate, right? So g conjugate is that piece, this piece is negative infinity gt conjugate, right? And then we put exponential, there should be a negative I omega t dt, right? But omega now is negative, so let me put a negative omega there. So this red formula equals this black formula, right? So that is g negative omega conjugate. It's kind of, you need to be clear on your mind, right? You need to be clear on your mind, but that's the equation. Right? Okay, questions so far? Okay, great. Great, gt omega, yeah. Okay, next we will look at the derivative, right? Let's look at the derivative. Let's look at the derivative. Let's take a derivative, the gt dg dt, right? Let's say dgt dt. Let's take a derivative, right? So let us use this equation, the inverse Fourier transform, take a derivative here. We'll take a derivative here, right? gt with respect to t. Then we will take a derivative on the right-hand side too. On the right-hand side, there is only one term with a t. On the right-hand side, there is only one term has a t, right? Exponential negative I omega t, t term there. So if we take a derivative, then we will have the 1 over 2 pi, 1 over 2 pi, and then negative infinity, infinity, right? And then take a derivative and the g omega, then take a derivative, right? So we need to take a derivative on the right-hand side, but on the right-hand side, there's only one term has the t. So that's basically, we take a derivative here, it's negative I omega, exponential negative I omega t d omega. Right? Okay. Okay, so we take a derivative on the left-hand side and then take a derivative on the right-hand side. That will give us the that means a Fourier transform of the derivative is this piece, right? So if you look at that, if I look at this equation, it is as if it is the left-hand side is time domain, right-hand side is the frequency domain, right? So this equation follow the inverse Fourier transform. And then we can get a conclusion that the Fourier transform of the time domain dgt dt is this red box, right? So that is the capital G omega and the negative I omega, right? So in other words, since we have this equation, we will compare to the standard inverse Fourier transform equation, we can get a conclusion that because it follows the inverse Fourier transform, and then this is time domain, this is frequency domain, that means if I take the Fourier transform of the time domain, I got the frequency domain. But so that means a derivative of the gt is capital G omega times negative I omega t, right? Okay. Now, what if I take another derivative? Let's take another derivative, gt second derivative with dt, square, and then this is 1 over 2 pi, negative infinity, infinity. Now, on the right-hand side, we'll take a derivative, right? We take a derivative on gt, and then we take a derivative on the right-hand side. There's only one term has the t. Now we take a derivative here again. So it becomes the second derivative. And on the right-hand side, there's still a one term has the t. Right? Still only one term has t. So we'll have the g omega, then negative I omega square exponential negative I omega t d omega. Right? Okay. So that means we only have the Fourier transform of the second derivative dgt dt. Second derivative is g omega I omega square, right? Oh, this is the g omega as a function, g as a function of omega, negative I omega square. Okay. Okay. So so now we have the we can conclude, we can further take a derivative, right? We can further take another derivative, and in that case, we can further take derivative, we can further conclude Fourier transform of the nth order. Let me write the equation here. We don't have the space. We can further take the, let me write here then. If I further take a derivative, so the Fourier transform of the dNgt dtn is g omega, right? Negative I omega nth order, right? So assume we have the Fourier transform pair. So assume we have the Fourier transform pair, and then we have the Fourier transform pair take a Fourier transform of the nth order derivative is going to be the Fourier transform g omega, capital G omega times the negative I omega nth order, right? We're going to use this property later on, but that's the Fourier transform of the nth order derivative. Likewise, we can take an inverse Fourier transform, right? We can take an inverse Fourier transform, and then we can take a derivative here, right? So we can take a derivative of g omega, but this time we'll take a derivative with the omega, right? dn omega is we take a derivative here, with respect to omega, with the it fall down, right? So this will be gt, g little t, and I little t nth order, right? Because once you take a derivative on the Fourier transform term, we take a derivative on g omega here, we take a derivative here, this only term has the omega is exponential I omega t. Then we take a derivative, each derivative we have one it falling down, and then we'll just put it nth order. Right? Okay. Okay, great. And okay, questions? Okay, great. Okay, the last one, right? So the last property. Okay, and okay. Now we have the Fourier transform of the g negative t, Fourier transform of the g negative t, right? So Fourier transform of the g negative t, right? So this will be the g negative t. Okay. So if we have the g negative t, we will just put the change the. Let me write it down. So it's the g negative infinity, right? And then it's the g negative t, right? And then exponential I omega t dt, right? So let's put the negative there, right? So if we put the negative there, that means it's negative infinity. It's actually, and then negative dt, right? So if t is substituted, then it will be negative, and positive will be flipped, right? So it's still g negative t, and then exponential I omega t, right? But now we have put a negative there. So let's put the negative t is replaced by negative t, and then omega need to be the negative omega. So the result will be g negative omega, right? G negative omega. So Fourier transform of a t in flipped, it will be the Fourier transform in the negative omega. Okay, so that's questions so far. It's just the Fourier transform, kind of review on what we learned from the signal systems, right? Signal systems. Yeah, it's now 11:06. We still have we still have time, and we will learn a material called Persevere's theorem. That's kind of also, we also learned that from the signal systems. We also learned from the signal systems. Okay. 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 So now we have first we define GT absolute value square. It's the signal power. Signal power in time domain, right? This is the signal power in time domain. And then we have the G omega, right? Capital G omega. Let me use capital G omega absolute square. This is called energy spectral density, right? It's the energy spectral density. It's the energy in the omega in the frequency domain. We want to, there is a Persevere's theorem says that GT in time domain, right? In time domain, all the power, right? All the energy equals the negative infinity, negative infinity to infinity, negative infinity to infinity, G omega absolute value square d omega over 2 pi, right? D omega over 2 pi, and they are the same, right? They're the same. So it's called Persevere's theorem. So P-S-E-V-A-L, Persevere's theorem. Okay, so this is Persevere's theorem. Let's prove that. Let's prove that, right? Let me use the board here. So let's integral gt absolute value square dt, right? So this is the left-hand side. It's the positive. It's the power in integral power in time domain. So let's write as negative infinity infinity gt conjugate, right? dt. So gt conjugate dt. Okay. So and then on our gt, so this gt conjugate we will substitute by the inverse Fourier transform. GT conjugate, we will so this piece will be substituted by inverse Fourier transform. So let me copy the same thing, the GT here, right? And then we will use the inverse Fourier transform. So it is 1 over 2 pi, and then we have conjugate, right? Integral negative infinity infinity conjugate g omega conjugate, right? G omega conjugate, then exponential negative I omega t become exponential I omega t, d omega, right? D omega. So let's make a conjugate, and then conjugate, right? Conjugate. So originally it's exponential negative I omega t. Now it become exponential I omega t, right? Negative become positive because of conjugate. Okay. Now I missed a dt, right? So I need to copy dt here. I need to copy the dt here. Okay, next we will change the integral order. We will change the integral order. Here, the first integral should be d omega, right? Now I would like to switch the order. We will move first 2 pi out. We'll move the 2 pi constant out. And then we'll move the g omega conjugate out, right? I will be a little bit lazy and let me do negative infinity, infinity, right? Okay, and then we integrate over t first. Negative infinity, infinity, exponential I omega t, dt, d omega, right? dt, d omega. Okay, so I switch the integral order, right? I switch the integral order. Okay, right? Okay, great. So now you will say, aha, we got this piece, right? We got this piece, and we compare this piece and the our original definition. What is this? It's the capital G omega, right? So you will see, did you see? Here is the little gt exponential I omega t dt, and then this will be capital G omega, right? This is a capital G omega. So it's 1 over 2 pi, negative infinity, infinity, g omega conjugate, g omega d omega, right? So then it's 1 over 2 pi, negative infinity, infinity, g omega absolute value squared d omega. Okay, yeah. So now we have the this derivation, right? So all the integral in time domain of the power, all the energy in the time domain, right? Power integrate in time domain. It is the same in frequency domain with a factor of 2 pi. With a factor of 2 pi, right? So in other words, if you take an integral in time domain and you take an integral in frequency domain, you're able to verify your results by what? By a factor of 2 pi. So if they have a factor of 2 pi, then your derivation is correct. Otherwise, there's something wrong, right? It's called Persevere's theorem. Okay, great. Okay. Any questions? Okay. Okay, great. So that's it. That's it for today's class.